it's okay. Thank you very much. It's okay.
Thank you. So the title of my talk is Uncertain Interconnections between Non-Commutative Algebra, Algebraic Geometry, and Brilli rings. And there are two parts of this talk. So first part is about deformations and associative rings. So usually people do deformations of commutative rings, but for some reason I really like non-commutative rings. And so I was interested in deformations of non-commutative rings and algebras, and I found some applications connected to some colleagues who do this research, who mostly do this research coming from geometry. So especially the first part of the talk is motivated by Michael Williams from Glasgow, who worked at the University of Edinburgh for several years and then moved to a prestigious position at Glasgow. And he works in geometry, but he's also a really good algebraist. Actually, he got an Oxford Prize for Algebra several years ago. And so this is the plan here is to mention some main definitions, then connections and questions of Michael Williams, who influenced my talk. Then the other will be applications of deformations of non-commutative rings suggested by other people. And in particular, I mentioned some new results, and which I obtained recently. And I would like to mention that at University of Edinburgh, we really have many people working in deformations. And for example, Johan Martens, John Pridham, and Arend Bayer work in deformations of commutative rings, and Ben Davidson and Ian Gordon of deformation of non-commutative rings. So I asked several people. And then the second talk is motivated by groups, by group theory. So it is about extending Lazar's correspondence outside of the context of the Lazar's correspondence, and it will be done in the context of Brilli rings. And I also mentioned some results of other people who did very important work recently in the context of Lazar's correspondence and Brilli rings. So here I would like to mention the formations. So first of all, if we have associative algebra, what is the deformation of this algebra? So we take a power series ring and we put new multiplication, which is associative. And when we put t equals 0, t is our variable of power series, then we obtain the normal multiplication on A. So obviously we can take just the power series ring, but usually we put different multiplication. And we want this multiplication to behave well, so this multiplication together with the addition on A gives on this set of power series the structure of AT algebra. So we can multiply by elements from of CT algebra, I'm sorry, of over the base key field. So basically it's not important, it's just natural connection. So if we have multiplication, this new multiplication, we can write A star B is AB plus U1 AB, that's some element from A multiplied by T plus some other element, which we call U2 from AB multiplied by T squared and so on. And if almost all UIs are 0, then the deformation is of polynomial type. So one question I was interested in is if there is a deformation, does it follow that there is a deformation of polynomial type with similar properties? So I mentioned some results which I got on the next slides. And here is the topic which comes from geometry. So people in geometry consider algebras when they can deform one algebra to another algebra, and we say that algebra A can be deformed to algebra B if there is a deformation of A, which at some point t equal s, so we specialize the variable at s, and we get an algebra isomorphic to A. So this is what they do. I would like to mention that geometric deformations and algebraic deformations are very closely connected. Usually, algebraic deformation implies geometric, but the connection is not exactly clear. Even Michael Wilms says it's a mystery to him. So here is the formal definition of deformation, so written in a proper way. So this is a new multiplication on a power series over the algebra A. So here first I would like to mention the work with Dave Bowman and Dora Pulic. Dave Bowman was 2 years ago my master degree student, and Dora Pulic was my PhD student, and she just defended her PhD this year. So we considered such question: when when can we deform a given algebra to concrete algebra A? So this question is motivated by questions of Michael Wilms, which I will mention a little bit in a second, a bit more what he's doing. And we, as application, answered the question of Michael Wilms. So that was published in International Mathematical Research Notices, and 1 year ago. So here is a simple description of our method. So in this talk, I don't really want to get into technical details, but this is the only thing which I explain. So we consider the polynomial algebra over our algebra A, which we want to deform to algebra A. And then we put x equal ta and y equal tb when A and B are from A. In general, in this method, we can put any function from any element from A of t on the right-hand side. And then we can calculate powers. So x squared will be t squared a squared, xy will be t squared ab, yx will be t squared ba, and y squared will be t squared b squared. And then we can write relations which follow from this presentation. So, for example, here we can see that x squared minus, well, maybe not immediately clear what are the relations, but we see which relations on the right-hand side are zero, and we put such relations on x and y. And then we have a factor algebra, which is our deformation algebra, and we can evaluate it and points to get the algebra A. So that's the general method. And just recently, actually the archive preprint with it appeared today. I put some extensions of those results, and I have one more preprint, which I will put soon on archive, is that some questions from Michael Wilms, which I mention in a second, were not possible to solve by our method with Dora and Dave. So I refined the method, which I called method 2 and 3. Method 2 was obtained from our method with Dora and Dave by removing some assumption, and method 3 was obtained by considering some algebraic extensions of A, and then it allowed us to have concrete N. And as an application of this method, I answered question of Michael Wims about deformations of 8-dimensional icons. Also obtain method 2 of deformation, and it also is interesting for Michael because he's interested in geometric meaning of deformations in general. So now, after explaining what I did, I would like to give a bit more details and a bit motivation when it comes from. So, as I mentioned, is motivated by Michael Wims' questions in algebras and geometry. So this is about 3 faults, that is 3-dimensional algebraic varieties. So several years ago, Michael Wims and Will Donovan developed a method for characterizing commutative rings which appear in algebraic geometry by using non-commutative ring theory. And the main tool there is contraction algebras, which basically give all invariants of those 3 faults and give amazing information. And here is motivation from Michael and Will Donovan. To understand the birational geometry, it is important to understand the flips and flops and to classify them, and to, in particular, to construct appropriate invariants. And the contraction algebra is actually invariant to every flipping or flopping curve in 3-dimensional algebraic variety. And it recovers all classical invariants. And maybe worth mentioning, this comes from research of Yama and Wims. The contractional algebras are factors of some quiver algebras obtained by them, and they come always from superpotential, as mentioned by in a result of Michael Wonderberg. And this is big progress, which I am very excited. Michael Wims and Gavin Brown, they characterized all contraction algebras by giving their superpotential, and as a consequence, there is a description of all those contraction algebras, which are also called icons, by giving generators and relations in purely algebraic form, and there are many algebraic questions which have meaning in geometry. So here are questions of Michael Wims, which actually have meaning in geometry, which he was very kind to give me, so I could do some algebra related to geometry. So his first question is: can a given icon, contraction algebra that is, be deformed to a concrete semi-simple algebra found by geometric method? So there are many of those icons, and it is quite technical to calculate those deformations, but we calculated with Dora and Dave one of the icons using our method, and the new method which I put on archive today, I think this should allow to calculate all the deformations, but it's very technical, so each of it takes maybe a week. So far I calculated one of the deformations and answer question about 8-dimensional icon. So those deformations to semi-simple algebras are related to Gom-Cooper-Waffa invariants. Actually, the semi-simple algebra splits into simple, and the dimension of those simple summands are the Gom-Cooper-Waffa invariants. And then another question asked by Michael is it true that a given icon cannot be deformed to other semi-simple algebra? And Ben Davidson mentioned that indeed, if it is true, and if icon deforms to only one semi-simple algebra, then there is like direct correspondence between GV invariants. Otherwise, there may be few possibilities for GV invariants depending on the deformations. And Michael also asked about question about geometric meaning of deformations to any algebras of icons. And here is a short motivation from geometry why deformations to semi-simple algebras are important. So Juan Toda showed that geometric deformations related to Atiach flop of the icon is semi-simple, and that's why the connections come from. And they don't know if their deformations are flat, but if there are algebraic deformations, then they would be flat, and that is the question. And so here, to question one, we constructed deformation for 9-dimensional icon and confirmed conjecture of Wims with Bowman and Dora Pulic. And just today on archive preprint, I put the archive preprint and calculated the dimension 8 icon using it. And interestingly, the deformation method which I presented today in the archive, which is method 3, is such that if we have any strongly flat deformation from algebra N to a semi-simple algebra, then it can be obtained using this method. Moreover, this method is of polynomial type, so that shows if there is strongly flat deformation from M to a semi-simple algebra, then there is a deformation of polynomial type from A to N. And also it deforms to almost all points to A. So this is this 8-dimensional icon. This is the smallest icon possible, and so I showed it can be deformed to this algebra, which is matrix 2 by 2 over complex numbers, and then a direct sum of 4 copies of the complex numbers. So here very quickly, other motivations of deformations. Deformations of commutative algebras obviously is very big area, I'm sorry, and because of connections with physics, so this is really huge area. Usually smooth commutative rings are considered, but non-smooth commutative rings is also of interest and maybe more related to methods of non-commutative ring theory, because we deform commutative ring to non-commutative. Here we have Hecke graded deformations of graded Hecke algebras, give information about Hecke algebras in representation theory. Symplectic reflection algebras give also deformation of some important classes of algebras, as showed by Ian Gordon. Deformations of modules over commutative rings in symplectic geometry determine intersection of geometric objects. So a colleague from University of Edinburgh, Jeff Hicks, works in this area. And there are some other connections. For example, deformation of Lie algebras can be obtained sometimes by deformations of related associative algebras, and this is used for classification of supergravity, also in algebraic geometry. Also, tomorrow Leandro Vendramin will talk at this conference, and he solved a long-standing open problem on Nichols algebras by considering deformations of some Hopf algebra. And Arend Bayer considered deformations of non-commutative algebras in algebraic geometry, and he says, this is another colleague from Edinburgh, that the division between commutative and non-commutative is not so strong nowadays in algebraic geometry. And here, well, is some motivation from Dave Bowman, who now does his degree at Bonn. He was my MSc student. And so this is about connection with physics, that if we would like study some model in physics, we would like it to be resistant to small changes. And actually, deformation theory studies exactly this topic. And that's why it's important in physics. So I just have a few minutes. I very quickly would like to mention groups, Lie-rings, pre-link connection. So first of all, there is a group of flows of a pre-Lie ring by Agrachev and Garmek-Lidze from 1981. It's very similar to the connection we mentioned by between derivation and automorphism on the talk of Fuksana, which was very interesting today. And so we have like E to A, but we always multiply from the left. And then we can have a multiplication, which has the same formula, but we put B at the end. And then this is a group, and this is construction of group of flows, which is isomorphic to the Lazar's group. So this usually for algebras over finite fields, but was generalized by Lazard, and not only Lazard, to finite pre-Lie rings. And actually, I mean, in the case of Lie rings by Lazard. And here we have a question, for example, if we have a Lie ring of cardinality P to n for a prime number n, does it follow the Lazar's correspondence holds for this ring? And we have, can it be generalized to 8 nil rings? And by result of Zelmanov, finite Lie rings, which are AD nil of bounded index, are nilpotent. However, it is not clear this index assures Lazar's correspondence holds. And here is a proposition of Giuseppe to appearing Journal of Algebra, that if we have a pre-Lie ring, then we can define the factor ring. If it has nullity index less than P over 4, then the Lazar's correspondence holds for the ring L divided by annihilator by P. And generally is possible to generalize it to more general structures. So here we have, if we have a Lie ring such that Lie divided by PL has nilpotency index less than P, is the analogon of the Baker-Hausdorff formula. And in the case of pre-Lie rings, if A to P is 0, then Ramp suggests that this correspondence between pre-Lie rings and braces, which worked one way for pre-Lie rings satisfying A to P equals 0. Well, I added some details because he just gave suggestion. And recently, Sennet-Rapiens showed in a full generality that every brace satisfying A to P equals 0 can be obtained this way. So I also work on this, but this is stronger than my result. So there is no correspondence between pre-Lie rings and braces. And Kurta Henko and Subotin developed new methods to investigate braces with given nilpotency index. And the group of flows always gives a brace. And this is the last result. So it's possible to have such generalization if we consider, instead of division by P, we consider a map from PA to A. And we apply this map instead of dividing by P. And this is the result we P in Journal of Algebra. If we have a technical condition that A to P is contained in PA and A to P is contained in I plus 1, then the brace A over annihilator pk is obtained by construction of generalized group of flaws from a Brillouin ring. And so that's it.